Hello student, in this video I'm going to talk about, or I'm going to continue from the last video. It is about hypothesis testing, and here you can see starting with the p-value or probability value. This is the probability of getting a value of the test statistics that is at least as extreme as the one representing the sample data, assuming that the null hypothesis is true. So it's a probability value whether we are going to get that value of the test statistics that is at least as extreme as the one representing the sample data, assuming that null hypothesis is true. Null hypothesis is rejected if the p-value is very small, such as 0.05 or less. If the value of the p is 0.05 or less, then we are going to reject the null hypothesis. We always test the null hypothesis. The initial conclusion will be one of the following: reject the null hypothesis or fail to reject the null hypothesis. So, traditional method, we have discussed this part. If the test statistics fall within a critical region, we will reject the it's not. This is null hypothesis. But if the test statistics doesn't fall within the critical region, we'll say that it is failed to reject the null hypothesis. P-value method is that we reject H naught if p-value is less than or equal to alpha, where alpha is significance level such as 0.05, or we can say that we fail to reject H naught if p-value is greater than alpha, where alpha is the significance level such as 0.05. Another option is that instead of using a significance level such as 0.05, simply identify the p-value and leave the decision to the reader. So we can directly give the p-value to the reader, and we can leave that decision for the reader is that whether they accept the null hypothesis or reject the null hypothesis, or they fail to reject the null hypothesis, depending upon the significance level of their own. Again, what is confidence interval? Because of a confidence interval, estimate of a population parameter contains the likely values of the parameter and reject a claim that the population parameter has a value that is not included in the confidence interval. Well, let's see through an example. Here, this is the diagram of finding p-values. What of the test? It might be left tail, right tail, or two tail. In case of left tail, p-value is area to the left of test statistics. If the p-value lies here, test statistics, there is test statistics, p-value twice this area, p-value should be twice the area if in case of left oriented two tail. In case of right oriented two tail, it should be inside the right part, twice the area. P-value is twice this area, p-value should be twice this area, and again here right tail, p-value should be this area. P-value should be equal to the area to the right of test statistics. This is the test statistics. Finding p-values first determine whether the given condition result in right tailed test, left tail test, or two tail test. Then find the p-values and state a conclusion about the null hypothesis. That is the procedure. A significance level of alpha is equal to 0.05 is used in the testing the claim that p greater than 0.25 and sample data results in a test statistics of z equal to 1.18. Second one is that a significance level of alpha 0.05 is used in testing the claim that p not equal to 0.25 and the sample data results in a test statistics of z equal to 2.34. In case of question 1 is this one. In case of 1, with a claim of p greater than 0.25, the test is right tail because we are going in that zone of in the right side of that is why greater than 0.25. The test is right tail. Because the test is right tail, the figure H6 shows that p-value is the area to the right of the test statistics. That is z is 1.18. Means p-value is there, and we refer to table A2 and find the area to the right of z is 1.18 is 0.1190. The p-value of 0.1190 is greater than the significance level of alpha 0.05. So we fail to reject the null hypothesis. P-value is greater than 0.05, because Z value, that 1.18, gives this value. And the p-value of 0.1190 is relatively large, indicating the sample results could easily occur by any chance. In case of second question, with a claim of p not equal to 0.25, the test is two-tailed, because we cannot go for greater than equation also, we can go for less than equation also. Because the test is two-tailed, and because the test statistics z equal to 2.34 is to the right of the center. Figure H6 shows that the p-value is twice the area of the right of z equal to 2.34. We refer to table A2 and find that the area to the right of z equal to 2.34 is 0.0096. So p value equal to 2.0096 is 0.0192, that is the p value. So p value of 0.0192 is less than or equal to the significance level. So we reject the null hypothesis. The small p value 0.0192 shows that the samples are not likely to occur by chance. So our final conclusion is that does the original claim contain the condition of equality? Yes. Then can we reject the null? Yes. In case of there is sufficient evidence to warrant rejection to the claim. No. Fail to reject. There is no sufficient evidence to warrant rejection of the claim. This is the only case in which the original claim is rejected. Here, no. We can does the original claim contain the condition of equality? No. In case of yes, we will go this solution. Here, that equation of original claim might be not contain any equal symbol. Original claim does not contain any equal symbol and becomes H1, because that is become alternate hypothesis. Do you reject H0? Do you reject H0? In case of H1, if the statement is H1, can you reject H0? Yes, only the sample data support the claim. Then we can reject the H0, and no, we cannot reject the or fail to reject H0. In case of fail to reject H0, then we can say that there is a sufficient sample evidence to support the claim, that is the original claim. This is the only case in which original claim is supported. So here in this case, directly we can say that original claim can be rejected, and here original claim can be supported. Some texts use accept the null hypothesis in case of fail to reject. We are not proving the null hypothesis. So the sample evidence is not strong enough to warrant a rejection, such as not enough to evidence to convict a suspect. So what is type 1 error? Type 1 error is a mistake of rejecting the null hypothesis when it is true. And symbol alpha is used to represent the probability of a type 1 error. That is a significance level. Type 2 error is the mistake of failing to reject the null hypothesis when it is false. So when the null hypothesis is false, but we are failed to reject, and it is type 2 error. But type 1 error is when the null hypothesis can be rejected. Mistake of rejecting null hypothesis when it is true. We are rejecting the null hypothesis, but we cannot actually, that is the null hypothesis is true, but we are rejecting it. Then it is type 1 error. But in case of type 2 error, we actually fail to reject the null hypothesis when it is actually false, which should be rejected. So example, assume that we conducting a hypothesis test of the claim p greater than 0.5. Here are the null and alternative hypothesis H0 equal to p equal to 0.5 and H1 equal to p greater than 0.5. Identify a type 1 error, identify type 2 error. A type 1 error is the mistake of rejecting a true null hypothesis. So this is a type 1 error. Conclude that there is sufficient evidence to support p 0.5 when in reality p equal to 0.5. So here type 1, in case of type 1 error, but it has stated that mistake of rejecting null hypothesis when it is true. So it is saying that here there is sufficient evidence to support P05, but actually if it is but evidence showing that P greater than 0.5 means we are rejecting the null hypothesis, but actually P equal to 0.5, actually the null hypothesis is true and the alternative hypothesis is false. So that is type 1 error. And type 2 error is the mistake of failing to reject, means if we fail to reject as P equal to 0.5 and therefore fail to support P greater than 0.5 when in reality alternative hypothesis is true. So we can draw the matrix here. The null hypothesis is true, null hypothesis is false, or what is the decision? We decide to reject the null hypothesis, but the null hypothesis is true, but we decide to reject the null hypothesis, then it is type 1 error. But we decide to reject the null hypothesis and the null hypothesis is false, then it is the correct decision. And again, decision is if we fail to reject the null hypothesis and null hypothesis is true, then it is correct decision. And if we fail to reject the null hypothesis but the null hypothesis is false, then it is type 2 error. For any fixed alpha, an increase in the sample size n will cause a decrease in P. B is the type 2 error. Or you can see here B is what? B is, this is beta, used to represent the probability of a type 2 error. Alpha is used to represent the probability of a type 1 error. So here it is controlling type 1 and type 2 error is that for any fixed alpha, if the alpha is fixed, then increase the sample size n will cause a decrease in beta. Beta means type 2 error. Type 2 error means when we fail to reject false null hypothesis. So fail to reject false null hypothesis can be decreased using large sample size. For any fixed sample size, suppose sample size is fixed, by decreasing alpha will cause an increasing beta. Conversely, increasing alpha will cause decrease in beta. So inversely proportional in case of sample size fixed. But if the sample size is not fixed, then we can and also alpha is fixed, then by increasing the sample size we can increase the beta. To decrease both alpha and beta, increase the sample size. So overall, if we can increase the sample size, we can decrease the both alpha and beta. The power of a hypothesis test is probability 1 minus beta of rejecting a false null hypothesis, which is computed by using a particular significance level alpha and a particular value of the population parameter that is an alternative to the value assumed true in the null hypothesis. That is, the power of the hypothesis test is the probability of supporting an alternative hypothesis that is true. So power of the hypothesis is nothing but is the probability of supporting an alternative hypothesis which is actually true. So as a whole, our whole p-value method is like this. We need to first identify specific claim or hypothesis to be tested and put them in the symbolic form. Give the symbolic form that must be true when the original claim is false. So if the original claim is false, the symbolic form must be true. Of the two symbolic expression obtained so far, let the alternative hypothesis H1 be one not containing equality symbol, so that H1 uses the symbol less than or greater than or not equal. Let the null hypothesis H0 be the symbol expression that uses the equal symbol and let be it fixed. Select the significance level alpha based on the seriousness of a type 1 error. So depending on a type 1 error, you try to fix the alpha level and make alpha small if the consequences of rejecting true are severe. So if the type 1 error creates more problem, then try to fix a small amount of alpha level. So that is why it's saying that make alpha small if consequences of rejecting a true H0, means if we reject a true H naught, then the consequences might be very high. Then we need to set the alpha small. The values of 0.05 and 0.0 are very common. Identify statistics that is relevant to the test and determine its sampling distribution, such as normal, t and chi square. Find the test statistics and find the p-value, and draw a graph show the test statistics and p-value, and reject H naught if p-value is less than or equal to the significance level alpha. Fail to reject H naught if the p-value is greater than alpha. Restate this previous decision in simple and non-technical terms and address the original claim. A confidence interval estimates of a population parameter contains the likely values of that parameter. We should therefore reject the claim that the population parameter has a value that is not included in the confidence interval. So we can reject a claim that population parameter has a value that is not included in the confidence interval. So here, suppose in this table you can see confidence level for confidence interval. If we put significance level is 0.01, then in case of two-tail test, our confidence interval is this one. One-tail test, that is 98%, and if the significance level is 0.05, then in case of two-tail test, confidence level will be this one, 95%. But in case of one-tail test, 90%, because the twice the region. And same way for 0.10 two-tail test, the confidence interval is 90% and one-tail test is 80%, twice the area of the confidence level. In some cases, a conclusion based on a confidence interval may be different from a conclusion based on a hypothesis test. See the comments in the individual sections. So try to understand that part. So we'll go through this next part of this section in next video. Okay, so till then try to go through the concept that has been discussed in this video, and some part might be confusing or not understandable, so then also let me know. We'll try to discuss it over Google Meet. And this type of study is very much important in case of doing research in any type of field, so it might be very helpful in your case also. So that's it. If you have anything to ask, then let me know. We'll meet over Google Meet. That's it. Thank you.